Okay, example 10, a rain gutter is to be constructed from a metal sheet of width 28 centimeters by bending up 1/4 of the sheet on each side to an angle of theta. How should theta be chosen so that gutter will carry the maximum amount of water? Make sure you add the y to your sheet so your words are spelled right. So anyway, 1/4 of the sheet on each side to an angle. So it's width is 28 centimeters, 1/4 of that is 7, so we're taking 7 centimeters and folding it up, leaving 14 centimeters in the middle. So it kind of looks like that, if you can imagine. All right, so what we're saying here is that this whole sheet here is 28, and we're bending it up by an angle of theta, and we'll make it a good, nice, symmetric gutter. We're not going to make some weird gutter where it's a different angle on one side than it is the other. And the amount we're folding up is 1/4, so that means this is definitely 7, this is definitely 7, and from here to here is 14. This segment I have drawn across the top here isn't actual material, it's just if you were to like create this trapezoid that we're looking at. That's the finished part of the trapezoid. Alright, so is everybody understanding what we're looking at here? So this red to this black to this red represents the initial piece of metal that got folded up to create our gutter. Alright? So our job is to figure out the maximum amount of water this gutter can carry. So what we're trying to do here is this sheet of metal obviously is like a flat sheet of metal, so when I fold this up I've got a three-dimensional gutter going off that in the back, right? The length of that gutter, in other words, if I'm going back this direction for the gutter here, right? That's not very good, but imagine that you got your gutter going back that way. That's not going to change. This distance here is not going to change. So if I can make this area maximum, I'm maximizing the volume of the gutter. Does that make sense? So basically all I have to do is maximize this trapezoid, and it has to do with the measure of theta. Because again, that's what they're asking us to do. What should we do about theta to make sure the gutter carries the most amount of water, the maximum volume? So, does everybody understand the problem for what we're supposed to do here? Alright, so let's go ahead and figure this out then. So, what I'm looking at here is a trapezoid, and what I need to do with a trapezoid, or what I need to figure out in order to find the area of a trapezoid, is base 1, base 2, and height. Those are the area components for trapezoid. And not only that, if I go ahead and do it right now, this trapezoid, area of the trapezoid, is going to be 1/2 the height times base 1 plus base 2. That's the area formula. Okay. Always for a trapezoid, half the height times the sum of the bases. That's how you find the area of a trapezoid. What I need to do is I need to find out the area in terms of what? Theta. Alright? So right now I got the area in terms of this base of 2 and this height. So where normally I just need to get one thing in terms of another, that's easy enough, right? But now I need to get both B and H in terms of theta in order to get this area formula all about theta. Alright, so what I want to focus on, if you look at this height that I've drawn in, it creates a right angle there, right? In addition, the top base and the bottom base are parallel to each other, which makes this red line a transversal to parallel lines. So this acute angle should equal this acute angle. So theta also lives up in that corner. It also lives over in this corner. If I focus on the left-hand side there, we're looking at a right triangle here, right? I'm just going to make an X right here just because we already got 4 variables, 3 variables. Let's just throw another one there just for fun. Okay, throw that X over there. Looking at this right triangle only, we're looking at a triangle that has a theta up in the corner, a 7 for a hypotenuse, an opposite side of H, and an adjacent side of X. If I look at my sine, cosine, and tangent functions for theta, sine of theta should equal H over 7. Cosine of theta should equal X over 7. And tangent of theta should equal H over X. Just using your basic opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent, sine, cosine, tangent ratios. Of the three, this one's not very helpful because it has too many variables in it. But this one here just tells me that if I cross multiply, h is equal to 7 sine of theta. This one here, if I cross multiply, it tells me x equals 7 cosine of theta. The other thing I want you to notice here, since I threw this extra variable x in, if I draw that height in right there, does everybody see that's the exact same triangle on the right that it is on the left? They're the same? So I can say this little piece over here is also x, and this is still h here, right? They're the same? All right. Looking at b sub 2, this is x, and this is x, and this right here is what? 14. So I can see that b sub 2 is just going to be 14 plus 2x. We just figured out x is equal to 7 cosine of theta. So I can make b sub 2 into 14 plus 14 cosine of theta. And just like that, b sub 2 is now in terms of theta. Also, we already have h equals 7 sine of theta. So now we have h in terms of theta. So these two facts right here allow me to go to h and b sub 2 and change those into theta expressions. So now I'm going to be dealing with theta compared to a instead of b and h compared to a. So the area of the triangle, what we're trying to optimize, trapezoid, is 1/2 the height times base 1 plus base 2, 14 plus all this stuff, right? So 14 plus 14 plus 14 cosine of theta, that makes 28 plus 14 cosine of theta. And then if I just take this 7/2 sine of theta out here and multiply it through there, that's going to give me the trapezoid. 7/2 times 28 is going to be 98 sine of theta. 2 and 28 is 14, 14 times 7 being 98. And then 1/2 times 14 cosine of theta times 7, so half of 14 is 7. 7 times 7 is 49, so we're going to get plus 49 sine of theta cosine theta. So just like that, we get the trapezoid area formula in terms of sine and cosine of theta. So now we've got what we need. We have our optimal equation in terms of a single variable, the variable we wish to figure out about. So again, if I was giving designs to the person making this gutter, I want you to turn this angle up this much to make a maximum because we figured it out using calculus. All right, that's what we're doing here. So, what kind of angle will I get if I'm using calculus? Radians or degrees? Radians, right? If I was giving directions to somebody folding up this sheet of metal, do you think the protractor measures in radians? They might make one like that, but usually they're in degrees, right? So what we want to do is get the radian answer, then we probably want to convert it to degrees. We'll deal with that when we get to the answer. So, anyway, let's take a look. Can everybody agree that theta probably is between 0 and pi over 2, though? Just looking at the picture. Imagine a gutter, right? If it's like this, that's 0. It's not holding any water, right? It's going to be falling off the side. So 0 is the bottom. This is 90 degrees or pi over 2. All right. If you go beyond that, now the gutter gets smaller, right? So it's probably between 0 and pi over 2. So I can just go ahead and assume there's an interval from 0 to pi over 2 for this, just using common sense, right? It's not a calculus rule or anything. I'm just thinking out, physical properties of things, and that seems reasonable. So I need to find the answers to this between 0 and pi over 2 where the derivative equals 0, because again, there's my endpoints, there's my function, so its derivative is going to be a sine cosine function, which means that it's not going to be undefined. So where that thing equals 0 is going to be what we're looking for. As far as finding the derivative of this, it's going to be a prime is going to be 98 cosine of theta That's just a basic sine function from the first term, right? No problems there. The second function is a product, so I'm going to say 49 sine theta is function 1, cosine theta is function 2, so I'm going to get plus 1d2. That'd be negative sine theta. Oh, what happened there? That's weird. So 1d2 is the function 1, 49 sine of theta times derivative of cosine is negative sine, plus 2d1 is going to be cosine of theta times derivative of 49 sine, which is going to be 49 cosine. I end up with a prime is equal to 98 cosine of theta minus 49 sine squared of theta plus 49 cosine squared of theta. And in its current state, it would be really hard to solve it, right? If I wanted to change sine squared into 1 minus cosine squared, then I got everything about cosine, then I can do a quadratic and form structure thing. I would probably, at this point, since I want this equal to 0, I would probably just put this in my calculator and let my calculator find out where it equals 0. So, just looking at time and stuff that's going to take to do things, it's easier just to go ahead and do it this way. So 98 cosine theta minus 49. And to do sine of theta squared, you do sine of x n parentheses squared. Make sure the n parentheses happened. If you don't put the n parentheses, it's squaring x and then sining it instead of finding the sine of x and then squaring it. So the n parentheses squared. And then plus 49 cosine of x n parentheses squared. My window is going to be from 0 to pi over 2. All I care about is where it crosses the x-axis, so negative 2 to 2 will be sufficient to be able to see that. Hit graph. Hopefully it doesn't cross a whole bunch. Hopefully it crosses at least once somewhere. Please. He's still thinking. There it goes. Oh good, I just checked. I thought it might have been in degrees, but I am in radians. So it crosses right there, and then it's done. So there's everything that we need to see. So if I want to find out where it crosses, hit second, calc 2, which is finding the 0. This is 0, this is 1.57, so minimum 0, maximum 1.57. I'm going to guess 1.2. And 1.1, how about that? 1.1961. In addition, again, another reason the graph way of doing this is nice is because then I can also see if I'm going from 0 up to 1.1961 and then from 1.1961 up to pi over 2, right? From here to here, it's above the x-axis, positive. From there to there, it's below the x-axis, negative. So I can already see the increasing, decreasing. Where the function lies, right, is above or below the x-axis. So we're hitting a maximum at 1.1961, which is what we're looking for, right? So theta equals 1.1961 radians is the right answer. But again, if I'm giving the directions to somebody to bend up a certain number of degrees, right, I want to change my radians into degrees. Does anybody recall how to do that? Conversion factor is for radians and degrees. 180 degrees is equal to blank radians. Here's 0, right? There's 180. How many radians is a flat line? I'll give you a hint, this was pi over 2. Pi. 180 degrees equals pi radians. So, if I have 1.1961 radians is equal, or times 180 degrees over pi radians, cancel, cancel, I'm just going to have to do 1.1961 times 180 divided by pi. So 1.1961 times 180 divided by 1.1961 times 180 divided by pi. 68.53 degrees. And again, 0 degrees was there, 68 about here, so that's your optimal gutter. Once you go beyond 68.53, the area starts decreasing again. So there you go. Alright, page there. Both of these, again, they got a little long. A lot of trigonometry in this one, and whether or not you remember it is going to be key to being able to do this. It's going to be basic SOHCAHTOA trigonometry. It's not going to go beyond that really, but again, the ability to change letters to the angles is going to be important. So looking at parallel lines cut by transversals, equal angles, you're looking for a right triangle with the angle you care about in it, opposite, adjacent, hypotenuse, that kind of stuff going on. So just be aware of that, and hopefully you can kind of remember all those from last year.